Hey everybody, and welcome to what I hope will be the conclusion of our lecture on functions, part 3. In the last lecture, we introduced function notation, f of x or f evaluated at x, and we learned that f evaluated at x was just another name for the variable y. We interpret f evaluated at x and y to be the same thing. Let's do a little bit more with function notation through examples. And let's compute the following. F evaluated at 0, f evaluated at 1, f evaluated at 2. And we might note that the domain of this function, let's see, what is the domain? Do we remember that? When we see a function defined like this, we start off assuming, one, that the domain is the entire set of real numbers. And then from the entire set of real numbers, we exclude any x value that causes division by 0 in this equation. Well, we're not dividing by anything, are we? So no value of x causes division by 0. And we also exclude any x value that will give us a negative under a square root or an even root. I don't see any square roots there or even roots. So the domain is the entire set of real numbers. We can take any real number and evaluate f of x at that real number. But to start off with, we'll evaluate f at 0. And here, at f evaluated at 0, 0 plays the role that x plays up here in our definition, or our model of f of x. So every place that we see an x up here in our model, we're going to put a 0 down here. 2, 0 cubed, minus 7, 0, plus 4. And that turns out to be 4. So f evaluated at 0 is 4. Another way of looking at this is that when x is 0, y equals 4. To the next example. This is f evaluated at 1. So this means that 1 plays the role here that x plays up here in our definition of f of x, or our model of f of x. So every place we see an x up here in our model, we're going to put a 1 down here. 2 times 1 cubed minus 7 times 1 plus 4. Oh, let's see, that'll be 2 minus 7 is negative 5 plus 4 is negative 1. So when x is 1, the y value is negative 1. Now let's do f evaluated at 2. 2 plays the role down here that x plays up here in our model. So every place that we see an x up here in our model, we'll put a 2 down here. 2 times 2 cubed minus 7 times 2 plus 4. Oh, 2 cubed is 8 times 2 is 16. So this is 16 minus 14 is 2 plus 4 is 6. So when x is 2, y is 6. Now let's try some things that are kind of tricky, but not really. We did this a little bit in the last lecture. Here we have f evaluated at x plus h, whatever h is. So x plus h is playing the role down here that x plays up here in our model. And every place up here in our model that we see an x, we're going to put x plus h down here. Now we have an x up here, 2x cubed. So where we see an x up here, we're going to put x plus h down here. This isn't so complicated. This is so easy. This is so easy, even I can do it. Okay, we see an x up here in our model. And so down here, we're going to put x plus h. Up here, we have negative 7x. Down here, we'll have negative 7x plus h. And then we also have 4. And you know what? I'm just going to leave it like this. I'm going to leave it like that. And let's see, maybe one more. You know what? That's kind of like what we did last time. Let me change things up a little bit. Let's do this. F evaluated at x squared. So down here, x squared plays the role that x plays up here in our model of f of x. So every place we see an x up here in our model, we're going to put x squared down here. So we have x cubed up here. So down here we're going to have x squared cubed. X squared plays the role here that x plays up here. So instead of having x cubed, we'll have x squared cubed. Then we have minus 7x. But x squared plays the role down here that x plays up here in our model. So instead of x, we're going to have x squared. Now, I guess I can simplify this somewhat easily, so I'll do it. We have something raised to a power, that whole thing raised to a power. Do you remember what the exponents do? You're right, they multiply. So this is x to the 6th minus 7x squared plus 4. Excellent, excellent, excellent. Now, you know, maybe I should do one more example. I think we need to see another example. It's kind of a special case, so I think we need to see this one done. This is a tricky thing. This is what we call a constant function. We have f of x equals 3. Now, if we did this in terms of y, this would be y equals 3. And do you remember what the graph of y equals a constant looks like? The graph of y equals 3 is just a horizontal line. Every point on the horizontal line has the same y coordinate. For example, let's say x is 1, or 2, or 3. X is 1, What's the y coordinate? Well, it's 3, because the y coordinate of every point on this line is 3. X is 2. So what's the y coordinate? It's 3 again, because the y coordinate of every point on this line is 3. X equals 3. What's the y coordinate? 3, because the y coordinate of every point on this horizontal line is 3. Well, you know what? The graph of f of x equals 3 looks exactly the same way. That we make no distinction between y and f of x. Y and f of x are two different names for the same thing. So this is what the graph of f of x equal 3 is going to look like. And when x is 1, what's f of x? F of x is 3 because the y coordinate of every point on this horizontal line is 3. So this is the point x equal 1, f of x equal 3. Okay, what about when x is 2? When x is 2, f of x or y is still 3 because the y coordinate or the f of x coordinate of every point on this line is 3. And when x is 3, f of x is 3 again. So this ought to help us understand how we can compute these values. Here's our model or our definition of the function. F of x equals 3. Here we have f evaluated at 0. So 0 plays the role down here that x plays up here in our model of the function. So every place that we see an x up here, we're going to put a 0 down here. What? Oh, there are no x's on the right side of the equation, so there's no place to put a 0 here. So I guess in a manner of speaking, every place that we see an x up here, we have put a 0 down here. You don't see any place where there's an x up here where we didn't put a 0 here, did you? So we've done exactly what we were supposed to do. If there are any x's up here, we put in zeros down here. And f of 0 equals 3. Well, I guess that shouldn't surprise us. That's the y-intercept of this graph, f of x equals 3. Let's do f of 1. 1 plays the role down here that x plays up here in our model. So every place up here that we see an x, we're going to put a 1 down here. Whoops. There is no place to the right of the equal sign where there's an x up here, is there? So there's no place down here where we can put a 1 in for x. F evaluated at x squared. X squared plays the role down here that x plays up here in our model. So every place up here that we see an x in our model, we're going to put x squared down here. There, that's it. And maybe some more practice. F of 2, f evaluated at 2. Every place we see an x up here, we put a 2 down here. And it works out exactly as we said it would. Didn't we say that when x is 1, f evaluated at 1 is 3? Well, that's what we got. Didn't we say that when x was 2, f evaluated at 2, the y coordinate was 3? F evaluated at 2 is 3. That's exactly what we're supposed to get. This kind of function sort of throws people for a loop because they say, wait a minute, where do I plug in the x? And the answer is, on the right side of this equation, there is no place to plug in an x. So we don't plug in anything. We just leave the right side of the equation alone. I'll have to tell you something. What I'm about to show you from here to the end of the lecture, I've never seen in any course other than college algebra or pre-calculus algebra. You won't see this sort of thing in a calculus text or, to the best of my knowledge, in any text higher than pre-calculus algebra. I've been teaching math for more than 40 years at the college level. I have never seen this, the sum function, the difference function, the product function, the quotient function. I have never seen these things outside of a pre-calculus algebra text. But we're required to have some homework exercises on these things. And we do have a common final exam that every section of pre-calculus algebra at Troy will take. And there will be exercises like this on the common final. So we will go over this. Learn this, know how to do it for the homework and for the test and for the final. But you have a better chance of getting hit by lightning twice than ever seeing this stuff outside of pre-calculus algebra. So we're learning this just for the homework and the tests and the final exam. If there's a sum function, I guess there's a difference function. Let's give this the once over and then we'll do the product and quotient functions. F plus g evaluated at x. Apparently that's mathematical shorthand for f evaluated at x plus g evaluated at x. This sort of turns out to be what we'd expect it to be. F minus g evaluated at x. That's the function f evaluated at x minus the function g evaluated at x. Now we'll look at the product and quotient functions. Here we have the product function, f times g evaluated at x. That's the same thing as f evaluated at x times g evaluated at x. And the quotient function, f divided by g evaluated at x, that's the same as f evaluated at x divided by g evaluated at x. Now, there are some things that I should mention here. In all of these examples, any x value that's not in the domain of f or any x value that's not in the domain of g is not going to be in the domain of f times g, or the domain of f divided by g. And the same thing goes for the sum and difference functions. Any x value that's not in the domain of f, or any x value that's not in the domain of g, is not going to be in the domain of the sum function. And any x value that's not in the domain of f, or any x value that's not in the domain of g, is not going to be in the difference function. And the same reasoning holds for the product function and the quotient function. With the quotient function, though, we have to dig a little bit deeper. Definitely, if there's an x value that's not in the domain of f, then it's not going to be in the domain of the quotient function. And if there's any x value that's not in the domain of g, then it's not going to be in the domain of the quotient function. But there may be some x values that are in the domain of both f and g that aren't in the quotient function. Can you think of a reason why that might be? Here's how we define f divided by g evaluated at x. It's f evaluated at x divided by g evaluated at x. Oops. And every time we divide by something, we have to make sure that we don't do what? The biggest sin in mathematics. We have to make sure that we don't divide by 0. So in addition to those x values that aren't in the domain of f, and those x values that aren't in the domain of g, we also exclude from the domain of the quotient function any x value that makes g of x equal 0. Normally, it's okay for a function g of x to be equal to 0. But here we're dividing by g of x. So any x value that makes g of x 0 causes division by 0 here. And we have to exclude that x value from the domain also. Let's look at some examples. Here we have f of x equal 2x squared plus 3x plus 1. G evaluated at x equal x squared minus 7x plus 5. And we're asked to find the domains of f of x, g of x, and f plus g of x. We start off doing what we always start off doing. We assume that the domain of this function is the entire set of real numbers. And then we do a couple of checks. Is there any value of x that causes division by 0 here? No, we're not dividing by anything, are we? Okay, so the domain is still the entire set of real numbers. One more thing to check. Is there any x value that would cause us to have a negative under a square root or an even root? There's no radical, no square root, no even root here. So that doesn't happen either. Our initial assessment stands. The domain of f of x is the entire set of real numbers. Now let's look at g of x. Oh. That we start off assuming it's the entire set of real numbers and then we do a couple of checks. Is there any x value that would cause us to divide by 0 here? Nope, because we're not dividing by anything, are we? Okay, second check. Is there any x value that would cause us to have a negative under a radical sign or a negative under an even root sign? No, we don't have any square roots. We don't have any even roots. So our initial assessment stands. The domain of g of x is the entire set of real numbers. Now the domain of f plus g. We exclude from this domain any x value that's not in the domain of g of x and any x value that's not in the domain of f of x. Well, there are no real numbers that fail to be in the domain of f of x. The domain of f of x is the entire set of real numbers. There's no x values that fail to be in the domain of g of x. The domain of g of x is the entire set of real numbers. So the domain of this sum function, f plus g evaluated at x, is the entire set of real numbers. Now we're not done. More. Let's say define. Okay, we're going to write this as a single function. And what is this? This is the same as f of x, f evaluated at x plus g evaluated at x, right? And we know what both of those things are. So this is 2x squared plus 3x plus 1. There's f of x plus x squared minus 7x plus 5. Here's our g of x. And we combine like terms. 2x squared plus x squared is 3x squared. 3x minus 7x is negative 4x. And 1 plus 5 is 6. So f plus g evaluated at x is 3x squared minus 4x plus 6. Now, let's compute f plus g of x for f plus g evaluated at x. Now we've already done that. F plus g evaluated at 2. Well, here's our model, our definition. 2 plays the role here that x plays up here in our model. So every place we see an x up here in our model, we'll just put 2 down here. 3x squared, we'll put a 2 down here. 4x, we'll put a 2 down here. Plus 6. Okay, 2 squared is 4 times 3 is 12. Minus 8 is 4 plus 6 is 10. F plus g evaluated at 2 is 10. Let's do another example, maybe this time with the difference function, okay? Here's a good one. F of x is, f evaluated at x is 3x divided by x minus 2. G evaluated at x is x over x plus 2. And we're going to find the domains. We're going to find the domains of f evaluated at x, g evaluated at x, and f minus g evaluated at x. First, the domain of f evaluated at x. The rule of thumb is to assume, starting off, that the domain is the entire set of real numbers. Now, is there any reason why we shouldn't stick with this assessment? Are there any x values that cause division by 0? Oops. X equal 2 causes division by 0. So x is not going to be equal to 2. Are there any x values that would cause us to have a negative under a radical? No, we don't have any radicals. So I guess we're going to have to modify our definition of the domain of f of x. We can say it this way. X is not equal to 2. When we say this, we're implying that x can be anything but 2. So this is one way to define the domain. Or we could do this in interval notation. Negative infinity to 2, together with the set 2 to infinity. The union of these two intervals is the entire set of real numbers minus x equal 2. So here's the domain of f of x. Now the domain of g of x. G of x is x over x plus 2. And we start off assuming that the domain of g of x is the entire set of real numbers. Do we have to modify this assessment? Well, let's see. Are there any x values that cause division by 0? Oops, x equal minus 2, right? X can't equal minus 2. Are there any other x values that we should exclude? Do any x values cause us to have a negative under a radical? To have the square root of a negative number or an even root of a negative number? Nope, we're not computing a square root or an even root of anything. So we modify our definition of the domain of g of x, and we say x is not equal to -2. Or we can write it in interval notation this way. The domain is the union of the interval from -infinity to -2 and -2 to +infinity. The union of these two intervals contains all real numbers except x equal -2. Now the domain of f minus g evaluated at x. Any x value that we exclude from the domain of f, we have to exclude from f minus g. Any x value that we exclude from the domain of g of x, we have to exclude from f minus g evaluated at x. So, let's see, here's our function. 3x over x minus 2 minus x over x plus 2. And we'll define the domain this way. We'll say x is not equal to -2 or 2. So by saying that x can't be -2 and x can't be +2, we're also saying that x can be anything but these two values. Or we could write it this way. The interval from -infinity to -2, -2 to +2, the interval from 2 to infinity. The union of these three intervals contains all of the x values, all of the real numbers, except x equal -2 and x equal +2. So we can denote the domain this way or this way. Well, I guess we have defined this, haven't we? 3x over x minus 2 minus x over x plus 2. You know, I'm tempted to leave it like this. We could get a common denominator and combine these two terms, but what the heck, I'll just leave it like this. Compute f minus g evaluated at 4. Okay. Here's our model. Every place we see an x up here in our model, we're going to put a 4 down here. We have 3x up top, so that's 3 times 4. We have x minus 2 on the bottom, so that's 4 minus 2. And then we have x up top. We'll put an x up, a 4 up here. We have x plus 2 on the bottom, so we'll put 4 plus 2 on the bottom. And what do we get? 12 over 2 minus 4 over 6. And we can reduce those babies, can't we? This is going to be 6 minus 2/3. And let's see, how many thirds is 6? 6 is 18/3. Okay. F minus g evaluated at 4 is 16/3. Let's take a look at a product example now. Here we're going to look at the product function, f times g evaluated at x. F of x equals 3x. And by now you all know the drill. We start off assuming that the domain is the entire set of real numbers. And then we do a couple of quick checks. Does any value of x cause us to divide by 0? Does any value of x cause us to have a negative under a square root? Nope. Okay. So our initial assessment stands. The domain of f of x is the entire set of real numbers. Now the domain of g of x. We'll go with the initial assessment that the domain of g of x is the entire set of real numbers, subject to further scrutiny. Our first check, does any x value cause division by 0? Nope, we're not dividing by anything. Okay. So far, our initial assessment of the domain stands. There's one more hurdle to cross. Does any x value cause us to have a negative under the radical? Whatever we have under the radical has to be non-negative, either 0 or positive. So we demand that x minus 3 be greater than or equal to 0. And that means, if we move 3 to the other side, that x has to be greater than or equal to 3. Or 3 less than or equal to x. We can define our domain this way and say x is greater than or equal to 3. In interval notation, we can do it this way. X can be 3. X is greater than or equal to 3, so x can be 3. And x can be any real number larger than 3. So in interval notation, this is how we would define the domain. The domain of f times g evaluated at x. Let's see, this is just f of x times g of x. And that's, let's see, f of x, that's 3x. G of x, that's square root of x minus 3. So here's f of x. Here's g of x. And we'll leave it like this. This is the definition of f times g evaluated at x. We want the domain of this thing. And we start off by saying it's the entire set of real numbers. Any x value that has to be excluded from f of x has to be excluded from the product function. But we don't exclude any x values from f of x. Any x values that are excluded from the domain of g of x have to be excluded from our product function. And what are we excluding? We're excluding all x values less than 3, right? So all x values less than 3 are excluded from the domain of g of x. So all x values less than 3 are excluded from the domain of f times g of x. The domain is all real numbers greater than or equal to 3, or we can write it this way. All real numbers in the interval 3 to infinity, including x equal 3. Compute f times g evaluated at 12. Here's f times g. F times g evaluated at x is 3x minus square root of x minus 3. So every place we see an x up here in our model, we're going to put 12 down here. 3 times x, ooh, but x is 12, times square root of x minus 3, but x is 12 here. Then we have 3 times 12 is 36. 12 minus 3 is 9. That's the square root of 9. Or 36 times 3, which is 108, I hope. F times g evaluated at 12 is 108. And let's do a quotient function example, and we'll be all set, okay? Hey, everybody, we have a nice example here. F of x is x plus 3. G of x is x squared. And we're going to be looking at the quotient function. F divided by g evaluated at x. First, we're going to find the domains of f evaluated at x, g evaluated at x, and then f divided by g evaluated at x. And then we're going to evaluate f divided by g of x at some number. So first of all, the domain of f of x. F of x is x plus 3. That's how f of x is defined. And we assume that the domain of f of x is the entire set of real numbers, subject to further scrutiny. First question. Does any x value cause division by 0 here? No. Does any x value cause us to have a negative number under a square root sign or an even root sign? No, we don't have any square roots. We don't have any even roots. So, our initial assessment stands. Let's look at g of x. Our initial assessment is that the entire set of real numbers is the domain. And by the way, when you do this for homework, if they want you to write this in interval notation, if they want you to write the domain in interval notation, do it this way, okay? The entire set of real numbers, that's the interval from negative infinity to positive infinity on the x-axis. Now, is this assessment right? Is there any value of x that causes us to divide by 0 here? Nope. So far, the ruling stands. Is there any value of x that causes us to have a negative value under a square root sign or an even root sign? Nope, we don't have a square root or an even root anywhere. So, the ruling on the field is confirmed. This is the domain of g of x. Now the domain of f divided by g evaluated at x. Any number that we exclude from the domain of f has to be excluded from the domain of f divided by g. But we didn't exclude anything from the domain of f, did we? So far, the domain of f divided by g is the entire set of real numbers any x value that we exclude from the domain of g of x has to be excluded from the domain of f divided by g. Have we excluded any x values from the domain of g of x? No. The domain of g of x is the entire set of real numbers. It's looking pretty good here. One more thing. Because this is a quotient function, we also have to exclude any x values that make the quotient 0. Do any x values make the quotient g of x equal 0? Ooh. X equals 0 makes the quotient 0, doesn't it? Okay. The domain of f divided by g evaluated at x is x not equal to 0. In other words, x can be anything but 0. And we can write it in interval notation this way. Negative infinity to 0, and 0 to infinity. So all of the x values in these two intervals make up the domain. Now, let's look at this from a different perspective. Let's actually write what this is. This is f of x over g of x. And that's going to be x plus 3 over x squared. And now that we see what f divided by g evaluated at x is, we can see right away that we have to exclude x equals 0 from the domain because x equals 0 causes division by 0. So with the quotient function, not only do we exclude from the domain of the quotient function any x values that we exclude from the domain of f of x, and any x values that we exclude from the domain of g of x, but we also have to exclude any x values that make g of x, which is the denominator here, equal to 0. Evaluate f divided by g, evaluated at 3. Here's our model. f divided by g evaluated at x is x plus 3 over x squared. Down here, 3 plays the role that x plays up here in our model. So every place up here that we see an x in our model, we're going to put 3 down here. In our model, we have x plus 3 on top. So we let 3 play the role of x here. 3 plus 3 on top. In our model, we have x squared on the bottom. Letting 3 play the role of x, we have 3 squared on the bottom. And that gives us 6/9 or 2/3. Okay, everybody, we are finally finished with this section on functions. Oh, it took us long enough, didn't it? But functions in general are pretty much the lifeblood of higher mathematics. If you go on to take trigonometry, if you go on to take calculus and so forth, it's all going to be about what we can do with functions and how we can apply them. So I said before we wouldn't see the sum function, the difference function, the product function, the quotient function outside of this class. And that's probably true. But in general, we will see functions for as long as we do anything that has anything to do with mathematics. So functions, we're going to continue to see and use those.